Hi everyone, welcome back to Emerge. And I see there are lots of people on Zoom today. So welcome. I'm E. Every time I repeat this, but please allow me to say. I'm E. I'm a PhD candidate in system engineering at Berkeley, and I'm the organizer of Emerge. Emerge is a dedicated platform for early career researchers who are pursuing academic careers, just like our speaker today, Zhe. And I don't think I need lots of introduction to Zhe. I think she is a close friend to many of us, and of course also a friend of mine. And Zhe is a PhD candidate in transportation engineering, and also is doing her master in computer science, advised by Professor X5. And a little bit senior than me, Zhe has always been a role model of me, and I think also a lot of other friends. And her work has also been recognized, including first place in the Informs post computation, and recognized at Rising Stars Award in Mechanical Engineering, ECS, and NSF CPS. So today, her talk will be on physics-informed learning and control for mixed autonomy traffic systems. So without further delay, please join me in welcoming Zhe for the talk. Just hand up to your screen.
Okay. Thank you so much, E, for great introduction. And let me switch to my slide. Right. Can people on Zoom see my slides?
No.
No?
yet.
Oh, okay. I think what? Oh, I know what's going on. I think I didn't share this. How about now?
No.
No.
Still no?
If you go to the Zoom window,
Mm.
then yeah, there, maybe desktop is easiest.
Oh, oh my God, the previous, your introduction also not shared.
It's okay.
It's
No.
okay.
Great.
Okay,
Perfect.
sounds good. Right, hello everyone, thank you so much for coming to my talk, and also hello people on Zoom, thank you so much for supporting me through online methods. As E introduced, I'm Zhe Fu. I'm a PhD candidate in transportation engineering at UC Berkeley. And I'm super honored to introduce my work about physics-informed learning and control in mixed autonomy traffic systems. And without further ado, let's cut into the problem directly. So intelligent mobility systems, including automated vehicles on the road, drone fleets in the air, and also emerging urban air mobilities, those are really complex systems operate in dynamic and multi-agent environments. And in the near future, or even currently what's happening right now, is actually with mixed autonomy. Like on the roads, we see both automated and human-driven vehicles. On the air, we see both autonomous and piloted drones. And in the planning for the urban air mobility, we can already include both unpiloted and piloted air taxis. So they're dynamic multi-agent environments. That means that it is consistently changing, and the interaction between human and the autonomous agents are really, really complex. And this complexity makes it really, really hard for us to understand, to model, to predict, or even further control their behavior. So how do we make progress? I think about this problem in three core challenges. First is about modeling. How can we capture the dynamics of the large-scale multi-agent systems? Secondly is control. How can we design strategies that steer systems with minimum intervention, especially for those decentralized, partially observed, and even including human systems? And thirdly, deployment. After we design those strategies, how can we deploy them with safety, robustness, and scalability. So in my PhD research, I actually tackle those three core challenges with three pillars. First of all is the modeling. And besides including the traffic and energy modeling work, I also try to propose a physics-informed machine learning algorithms, which is the neural finite volume method that can tackle the solution of the hyperbolic partial differential equations. And on the second pillar, control and safety algorithms, I designed some performance-driven algorithms, including the kernel planning and imitation learning control for autonomous vehicles, and some safety critical algorithms, including neural control barrier function and unsupervised anomaly detections. And for the experimental validation work, I try to validate all those control algorithms into a large-scale operational test, including 100 autonomous vehicles deployed on the I-24 highway. And also, I tested some safety-critical algorithms with drones. And another interesting work that I did is we used the driving cars as a data collector, try to gain some vehicle level trajectories using the car that we drive. And we build these data sets trying to showcase the Bay Area stop-and-go ways. But today, I cannot cover all of them into a 40 minutes talk. And specifically, I pick a cutting point for today is the mixed autonomy traffic systems, specifically on the road, where automated and human-driven vehicles coexist and interact on the road. And specifically, I will firstly talk about the initial model we try to use to model the traffic and energy, and the kernel planning and imitation learning control strategies that we designed to try to use autonomous vehicles to guide the human drivers. And I will talk about how we apply those algorithms into the 100 autonomous vehicles test. And then through that test, it motivates me to revisit the modeling because it actually helped me to understand how important that layer of the work is. And specifically, I will present you the meat of today, which is the physics-informed machine learning technique that we designed to solve the hyperbolic partial differential equations. So let's start the journey. I'm always motivated by how can we actually achieve the efficient mobility through autonomy. So through the 2022 US Environmental Protection Agency, we can see that the transportation sector is the largest contributing sector of greenhouse gas emissions. And it's actually occupy about 28% of the total emission in the US. And in 2016, a seminal paper provided by the University of Washington, they pointed out that vehicle automation may be able to help reduce energy consumption with proper and carefully designed strategies. So that motivates me about the question, can we actually use vehicle automation to help achieve the efficiency of the mobility system? So let's take a look at the most common phenomena in traffic jam. On the left-hand side, it is a video showcasing the stop and go ways, which everybody will experience when you stop in traffic. And most surprisingly is that the stop and go pattern usually not caused by road closure or bottleneck or accidents. It actually just happened because the way we human drives. And so those stop and go ways actually contribute to a large portion of the emissions that I presented before. And it will also waste a lot of fuel and also make the trips longer and pumping more emissions into the air. So through our research, we tackled that problem directly using a few autonomous vehicles to drive smarter to smooth the traffic flow so that to cut the emissions and energy consumption. And let's visit the current mixed autonomy stage. First of all, like the current automation level is about level 2. So according to the SAE, they divided the automation level into 5 different levels, while the level 5 means the fully autonomous vehicles. So level 2 means that your car just equipped with adaptive cruise control, which is most of the market sell car right now have that ability. So it's it's the level 2 adaptive cruise control level automation. And besides that, only a few automated vehicles are available on the road. And besides that, different brands of the car manufacturers, they actually have different sensing and actuation abilities. So that together brings us a question. Can we utilize this very limited number of partially automated and heterogeneous vehicles to stabilize traffic conditions for all vehicles within the system? So not just the control vehicles, but all the vehicles. So let's simplify the problem with this setup. Let's take a look at just single lane here. As I mentioned, only a limited number of cars we have the ability to control, and we mark it with the red car. And for those red cars, it has ability to sense what's going on right in front of it. So we mark those the leader car of that as the blue one, and we call it sensed human-driven vehicles. For the rest of the car in the system, they're just the white one, and they're just the other human-driven vehicles that we don't have ability to control, and we also don't have any information from them. And we also need to define some states, like what kind of information we can extract from the system. And first of all is the macroscopic observations, which we call it local states. It includes the position and the velocity information from both the car that we control and the car that we sensed. And besides that, because of the road infrastructure, for example, the loop detector, the radar, or some camera on the road, we might have some ability to obtain the macroscopic traffic state estimation, which is the global states. Those information sometimes can give us, for example, the average speed of all the vehicles within a segment, which is an indicator for us to know, okay, maybe that segment has some congestion over there, but that segment is the free flow speed. And we define 3 different sensing paradigms. The first one is global sensing, which means it equipped both the local states and global states. And the local sensing, which is just the local states. And there is a very interesting paradigm, which is the semi-sensing, which exactly happened in our 100 autonomous vehicles test. In that case, we got access to the control car. We have the access from the road infrastructure that we have some macroscopic traffic state estimation, but we don't have access to the sensed car. So yeah, later I will give more details about this sensing paradigm. But here, I think you already have a good foundation that we can proceed. So in this project, I also follow the 3 pillars: modeling, control, and deployment. For modeling here, we initially just use some existing work. For example, for traffic, we utilize the INRIX data, the real-time data, to help us understand what's going on in the downstream and what's going on. We also designed some algorithm to kind of do a simple prediction. And because as I said before, the ultimate goal for this project is to reduce energy and energy consumption and emissions. So we need an energy model to estimate as a proxy to evaluate how effective our algorithms are. And this model is based on the autonomy software by Argon Lab, and we conduct some chassis dyno validation collaborated with Toyota to validate the model that we developed. And for each of the sensing paradigm, I actually designed different control algorithms. For global sensing, I designed the kernel-based feedback control, which is a model-based control strategy. It used kernel planning for target speed design And it leaves the gap regulation for vehicle level. So it's a technically 2-layer hierarchical control. And for the local sensing paradigm, the main innovation here is because for this setting, our goal is not to mimic human, but we want to actually teach human to drive in a better way. So definitely we are not using imitation learning to as a common strategy to mimic human. Here we actually consider the kernel-based feedback control as the expert in the imitation learning setting. And in that case, we reduce the input, we get rid of the input relying on the macroscopic traffic state estimation. Why? It's because not every road we have access to those in-race data and or those in-race data may be unreliable at all. So I tested these 2 control strategies in both single and multi-line simulations. And it proved that it can achieve, on average, over 15% energy savings with only 4% autonomous vehicles deployed in the system. But later, as I said, when we try to deploy that into the 100 autonomous vehicles tests, the sensing paradigm changed. It only have the eagle state and the traffic state estimation. But we adjusted really quickly. We actually still kept the hierarchical level of the controller. We try to gain the target speed through the traffic state estimation as a speed planner, and we broadcast that high level speed to the car, and then leave the rest of the the gap regulation, safety things to the learning-based controller as the vehicle level control. And we test that with the MegaVanderTest, where we deploy 100 autonomous vehicles collaboratively controlling 4 miles of freeway over 3 hours during the morning commute. And that has to last for 5 days, from Monday to Friday. And as you can see, on the right-hand side, this is a I-24 motion system, mainly developed by Professor Dan Work at Vanderbilt. It covered 4.2 miles of a segment on I-24 highway. It has 276 4K resolution cameras. Why we need that is because the overall goal of this project is we want to actually achieve a system level energy saving. And but we have no way to actually get information from the rest of the human driven vehicles. So we need a camera to catch the behavior of the rest of the vehicles, and we use computer vision technology to extract all the trajectories from those video footage, and then we can evaluate their energy consumption using our energy model. And so during the MegaVanderTest, it's not just I pushed my code into the cart, then that's it.
A clarifying question for you.
Sure.
The cameras placed along the highway, when you're capturing the trajectories, are those being fed back into the decision making of the autonomous vehicles themselves, or are they just being used for the evaluation of the human-driven vehicles?
During that test, it's only for evaluation. Yes.
Thank you.
But actually, there is some feedback loop because our car is randomly distributed, and our cars keep sending some data points back to our server. So those cars is actually acting both like a sensing car and as a control car. Yeah. And
But by the way, since we had that question, if I may insert, you can be modest. I don't have to be modest about your work and this team's work. This is the largest traffic experiment in history.
okay, got it.
Period. So it's, yeah, whereas other researchers might have little toy cars in their lab that are doing traffic experiments. This is on real roads, on the highway, 100 vehicles with drivers that you all recruited. Yeah, so this is, yeah, credit to you and this team. Largest scientific traffic experiment in history. Full stop.
Got it. I will definitely include that sentence.
Yeah, you can be modest, but I'll be less modest.
Cool.
Invite sponsor to every copy you attend.
Yeah.
Yeah, I will definitely. Yeah, coming. All right, yeah. this is just like, I want to show you how we did that, like we trying to install and uninstalling hardwares on the 100 cars parking in the parking lot of the headquarters. And this is actually, yeah, a view of like how we manage the fleet. And I also want to give you a little bit like sense how a normal day for me looks like during the test week.
Love it.
So like I actually have to woke up at 4 a.m. in the morning because I have to be in the parking lot at 5 a.m. starting to gear check for all the drivers for those 100 cars. Yes, we have drivers for them because we want to ensure safety. And I mentioned that those cars are level 2. They are not fully autonomous. And then after sending the first batch of the drivers, I have to go back to the headquarters to monitor the test and also detect possible bugs. And then I will try to refine and improve the controllers and deploy the new algorithm into the test cars. And then I will go out to test the control algorithms in the early afternoon. And this probably need to go several rounds, until in the late night, we can deploy the new algorithms ready for tomorrow to all the 100 cars. So I was right now I will show you some really high level results. So through the I-24 motion systems, we actually, this is I think the largest time space diagram generated by that systems. And it covered, as I said, 4 miles of the segment over 3 hours. And using those trajectories, we can calculate the vehicle consumption for each of them. And we found that in both shockwave and free flow scenarios, over 10% fuel saving achieved through our control strategies. And on the right-hand side, I want to show you the plot to show each of the vehicles' fuel consumption versus the distance between itself to the nearest of AVs. And it shows that the nearer the human-driven vehicles to the AV are, the more fuel efficiency they could gain, which further validates the effectiveness of our control strategies. So through this project, I will actually picture each of the stage as we firstly begin with some real-time traffic data. We try to generate some target speed suggestion for the vehicle to deploy. And we ask the leader vehicle to do the control. And in the end, we want to smooth the traffic flow. But this success actually relies on accurate, timely target speeds design.
Can I ask just quick clarification? Do all vehicles receive the same target speed?
No. Because the target speed is actually speed profile. It will change, depends on position. So different vehicles setting in different position will receive different target speed.
So the target speed varies by space and time.
Yes. So, but as I said before, the data that we gain usually have the communication delays and losses, and it's incomplete or outdated. This actually really motivates me to think about how can we actually get some accurate traffic estimation and traffic prediction. And this leads to how do we model the traffic flow effectively? Let's take a look at how people do in the past to do the traffic flow modeling. And back in 1950s, there is a seminal model called LWR model, which is a first order parabolic partial differential equations. And in 1970s, the PW model was proposed, which is a second order traffic model, adding the momentum equation back to the conservation law. And in the 2000s, the ARZ model was proposed further to revise the momentum equation, and it has a better ability to capture the stop and go waves. All of these models are hyperbolic PDEs, but those PDEs are super hard to get the solutions. And why? Because first of all, those solutions are usually contains a lot of shocks and discontinuities. Oh my god, discontinuities. And
Good, better than Trump and Tylenol.
And the hyperbolic PDEs also include many weak solutions, but among all the weak solutions, there is only the entropy solution is physically valid. And like in the past, people usually use the finite volume methods to solve these hyperbolic PDEs. However, as you can see on the left-hand side, I show you six different numerical schemes with the exact solution showing as the blue curve over there. You can see that the traditional solvers, especially LexFridges, they have the tendency to over smooth those shots. And like although like some of them, for example, the DG, which is a finite element method, it can actually match pretty good for most of the like occasions, but it require like extremely fine meshes and also require really high computational cost. So that actually brings me to the question, can we design neural network-based solvers that match or even surpass those finite volume methods in accuracy, but while keeping the cost low? Let's take a look at what is the current stage of the neural network solvers. First of all, people think about the supervised neural network solvers. It directly learns from the data, but it struggles with discontinuity. Oh my god. And some physical constraints. And some popular architecture include convolution neural networks, graph neural networks, and neural operators. And but like sometimes we may not have the exact solutions to learn from. So people saying like maybe we can come up with some unsupervised neural network like solvers, and maybe we can also benefit from embed those PDE structure into the loss. So like, but the problem is that like a very well-known work is the standard pins. But the standard pins actually fail on some like hyperbolic PDEs with shocks, and it still lacks theoretical guarantees in shock-dominated regimes. So in summary, the limitation of the existing neural network solvers are like they're struggling with preserving regularity, finding the entropy solutions, and also preserving the conservation laws. So that's motivated us to propose a neural finite volume method, which should preserve essential PDE properties, and we hope that it can match the computational cost of the finite volume schemes. And also, we hope it can support both supervised and unsupervised learning to kind of cater different situations. And we want it to be generalizable so that it can be extensible to higher order space or time and even field data, not just the PDE's embedded data. So before I dive in to introduce our neural finite volume method, I want to give you a little bit background about the finite volume method because our method is largely based on that architecture. So for finite volume method, we will firstly discretize the space and time into different cells, and we will calculate the average value within that cells. And here we use the density as an example. And then how it works is actually it's based on this update rule developed through the conservation law. It will try to actually obtain the numerical flux between different cells and plug that in so that it can evolve and obtain the next time steps value. Specifically for first order like hyperbolic PDE and like a first order finite volume schemes, we only need three cells, left, middle, and right. And as I show in here, it can evolve alongside the space, and then with the update rule, it can obtain the next time steps value in the middle. So then it actually shifts us to the key element, which is how we estimate this numerical flux. So in the past, for those numerical finite volume methods, there are all handcrafted numerical flux, and here I show you the good enough scheme, which is we are no one first order, but like it can converge to entropy solutions. And for us, we actually propose that let's use a neural network to kind of estimate this like a big F here. And specifically, what we need for the first order is just like the two like row on the left and right, and then it's trying to estimate the flux between the two cells. And here I want to show you how it actually works on the high level. So space-wise, we firstly kind of discretize the traffic into different cells as is shown here. And for here, we use the cell 3 and cell 4 as example. We plot those like density as the input, and then through the neural networks, we obtain the numerical flux between the cell 3 and cell 4, and we feed that into that update equation. And simultaneously, we can also compute the numerical flux between cell 2 and cell 3 and feed that as this variable. In this case, with this update rule, we can successfully get the next prediction like value for the cell 3. And like it can be like do in parallel for the whole like space within the same time step. So time-wise update is actually follows exactly as the finite model method. As I said before, illustrated before, space-wise, it's like at the same time step, we use the neural network to obtain the numerical flux between each of the boundary of the cells. And then with the update rule, we obtain the next time step's density. But like as I shown here, this one, we have no way to get it, so we fit in the boundary condition. And it keep like evolving using the same strategy I introduced. And like it keep evolving time-wise. So like now you have the high level how it will work, but what specifically we designed for that neural network? Actually, it's like surprisingly really simple and small convolution neural network, just 1D, and it includes only 1,200 parameters. And besides that, our neural finite volume method support both supervised and unsupervised learning. For supervised learning, we actually train it on several different Riemann problems. Those Riemann problems are initial value problems with two constant states separated by discontinuity. Oh my God, this word, I really need to practice on that. There are simple cases, and why we chose that because that's the case that we can have the exact solution on. And like for example, like in traffic, those Riemann problem like can bring us different cases like shock waves and refraction waves as shown here. And I want to like mention that specifically mention that we train on the Riemann problems, but we tested on much more complex cases beside like beyond Riemann problems. And for the unsupervised schemes, we actually learn from the weak formulation loss over the Riemann initial conditions, as this like a loss function shows. And this actually includes like a set of suitable test functions, and it can be a set of like compactly supported polynomials. And as I said before, like it's over different Riemann initial conditions, and we randomize through like over 1,000 cases.
So sorry, a clarification question here. So here's a loss function. Previous slide also a loss function.
Yes.
So this one is much more scary. So what happens here? Yeah. What's the connection or the difference between these two slides? The loss function on this slide and the loss function at the next slide.
This is the supervised learning, which means that
Okay.
which means the U like is a solution from those Riemann problems.
Oh yeah. I missed that point.
Yeah.
Right.
But this one is in this case we don't have any like solution, any data at all. It's just like we know how the PDE looks like. So we just like formulate the PDE into the weak formulation and embedded that to the loss function. Yeah. Thank you so much for the question, like clarification question. And so yeah, now you know the architecture and how it looks like for the neural network that we developed. Let me show you some like results. So we actually benchmark our method on several different PDEs, and we specifically pick two categories. First of all, is the LWR model in traffic, and the other one is the implicit Burgers equation. And I also want to point out that for LWR model, it's embedded a flux function over there, and different flux function actually leads to different in traffic theory we call fundamental diagram, which represent different way of the vehicles like dynamics or the traffic system dynamics. And like people propose different shape of the flux function or the fundamental diagram, including Renshaw, Greenberg, trapezoidal, underwood, triangle, or like skewed triangle, like shown here. And if we like embed different flux function into the like equation, we actually got different PDEs. So here, I just want to like give you like a high level impression. And we try to actually try to compare our methods prediction with the ground truth. And for here, the ground truth, we obtained it through the last half formula. We tested on 6 different like LWR flux functions. And as you can see, like it actually matches with the ground truth visually. And quantitatively, I want to give you some numbers, but don't like focus on that. I will like explain to you one by one. So first of all, as I said, we actually test on 7 different PDEs, including the 6 variants of the LWR and the Burgers equations. And we have both our supervised scheme and the unsupervised scheme here. And we compared and chose several different numerical schemes, the finite volume methods, and one like finite element methods as the benchmark baselines to compare with. And for the first order finite volume method, we specifically can compare with the good enough schemes. And as you can see, we can like definitely beat the first order finite volume method. And we also consider some higher order finite volume method, including ENO and MINO. And as you can see, like our accuracy is at the same level, although sometimes it might like slightly less than the ENO and MINO.
Sorry, can you say something for clarification and to emphasize the contribution here? Can you say something about the discretization size of the baseline methods versus the neural methods? I imagine importantly with the baseline methods, you have a very fine discretization maybe in space and time, but maybe with the neural methods, you have a coarser discretization?
That's a really good question. So yeah, clarification is that our method has exactly the same discretization with the first order finite volume method.
Okay.
But like for the higher order finite volume method, it includes more stencils because ENO and MINO, like for example, for the first order, it has like 5 stencils to consider. So the discretization for them are the same, but like higher order one needs more input. While DG, as I said, like as you can see, like if you just compare the number, no, we are not like able to rival the accuracy with DG. But DG itself require a lot more like effort about like discretization and all the implementation. So it requires much higher computational cost. For here, we want to include it is because it's state of the art. It can provide really high level accuracy. And a spoiler alert, later I will introduce a extended version of our method that can rival the accuracy of DG while still maintain the first order complexity of the final volume method. Thank you so much for giving me the opportunity to introduce the spoiler alert. And here, I just want to give you like an easier way to understand the numbers before. It's we introduced the method of win rate, which means the number of evaluation set that the row like scheme can outperform the column scheme. So again, like as I mentioned previously, our both supervised and unsupervised methods can beat the first order final volume method, while like rival with the Eno and Reno, like the higher order final volume method. But like unfortunately, in terms of this version, the accuracy cannot beat with the DG. And for here, I think it's also really important to emphasize the convergency of our method. So this two convergence plot shows that we like both the supervised, which is the red curve, and the unsupervised, which is the green curve, comparing with the good enough scheme, which is proved to be converged to entropy solution, along like with the finer and finer like time discretization, our like L2 error is still like keep lower than the good enough scheme, which gave us the confidence that it will converge to the entropy solution. And here is like how we actually can showcase our method's flexibility and generalizability. Is that we can actually extend the input size, not just spatially, but time steps wise. And as far as I know, all the classical numerical schemes don't have that capability. They cannot incorporate several different time steps. But for us, it's very easily, because of the neural network structure, like inherently can include more time steps. And another thing that I need to point out is after we actually extend that into like 5 time stems and 5 stencils, it only increased the size of the neural network around like several hundred of parameters. So it's still within like 2,000 parameters. And the way it works is still like similar as I introduced before. It's just like we increase the input size of the neural network, but it still provides us the approximation of the flux between the cells. And we use the same like update rule to obtain the next prediction of the density.
So it's kind of like you have a larger perception field analog to CNN by extending these cells.
Yes.
I see.
Yes. So here I want to show you the initial results that we obtained with just extending our method with 5 time steps and 5 space steps. Yes. And on both Burger's equations and LWR equations, as you can see, now we can actually very closely match with the exact solution in the shocks way, in the shocks portion, while the good enough actually over smooths as the green curve shows here. And here I just want to show you the video to show to like let you know that it actually keep tracking the exact solution along the time. It's not just like I pick a time slab like showing you that it's only matched at that point. And here it comes with some like quantitative results. So like for here with just extending to the 5 time stamp and 5 space time stencils, our like accuracy like can actually be can actually be like up to like 10 times better than our previous like Valina like variant. And now it's actually very close to the accuracy of the DG. They are actually at the same magnitude right now. And even for yes, they're at the same magnitude. And so besides those like synthetic PDE data, we also want to showcase that our method can be applied and accurately predict in the field data, which is really noisy and complex. So we firstly try to apply that method to drone capture highway data, which is the data set we obtained by our lab, using the drone on the highway segment in China. And it includes like 12 videos recorded by a drone and 15 minutes of the data. And as you can see, there are 4 visible stop and go waves. And maybe this plot is like can show it more clearly with the time space diagram. And for this case, we actually use the very last portion of the wave. It's about like 70 seconds of the data, which just like 8% of the whole data set, to train our model. And then it's generalized to the full data set to test on the rest of the 92% of the data. And for here, I want to firstly show you how those baseline, like those numerical schemes work in this situation on this data set. And for the column, for the row, they are representing 5 different finite volume methods that I showed before. And for the column, it shows different flux functions that we are trying to plug in. And as you can see, compared to the ground truth on the right-hand side, although some of the model combination, they can capture the trend slightly like this, all of them actually failed on kind of predict the traffic in this setting. And here I want to show you how our Berliner version of the method and the extended version of the method comparing with the best finite volume method result we can obtain through the previous steps and the ground truth. As you can see, the best one that we obtained here is the Wino scheme with the triangular flux function. Although here it captured the trend for the 4 waves, but you can still see some very significant glitches here. And for the Berliner version of our method, in terms of the accuracy, it can definitely beat with all the baseline. But I have to admit that it still has a problem here. It initially, after we fit in the initial conditions, it thinks that the wave will continue to kind of evolve. You don't have the ability to kind of anticipate that it will dissolve in the future. But after we incorporate more time steps, it has the ability to actually detect that it will dissolve in the future. So
and clarifying questions, these are the neural finite volume. This is the supervised or unsupervised? More specifically, is the loss function fitting just to data or a combination of a PD model and data?
That's a really good question. So here, we only use the supervised version because there's no need for us to use the unsupervised. We have the data over there, and we actually want to fit with the data better so that for those numerical schemes, they are all based on the model itself. But we all know the model itself also has some the model is not fully correct also.
Yeah, it's an idealization.
Yes, exactly. So yes, the neural finite volume method here in the real data set setting, we use just supervised.
A clarifying question here. So your prediction has a time dimension, right?
Yes.
So I want to understand, is all the prediction made just by information at t equals 0, or you
Yeah, that's a really good question. If I have more time, I will show you the details. But in short, we just gave the initial condition and the boundary condition. And then all the prediction is auto-regressively.
boundary condition here?
Boundary conditions means just on the
the flux of traffic at the beginning of
the beginning and at the x equals to 0 and x equals to the very last. Only that
I see.
Yeah. Because we need that to evolve to the next time step. Yeah. And then besides that, we also try to scale up and try to see how powerful our method can be. Because previously it's just 15 minutes of data. So we tested with the data that we collected from the I-24 motion through the largest in the history mixed autonomy field test. And this data set actually include 10 days of data over 40 hours of morning rush hours. And it includes 200 gigabytes of JSON file and over 600,000 vehicle trajectories. And for us, we actually only train on 1 hour of the data of 1 day. And it's only around 2.5% of the data set as the training set. And then we generalize it and predict on all other days. And here I just want to show you it actually generalized pretty well and comparing to the ground truth over there. And we also compare with the good enough prediction. As you can see, the good enough can capture some like trends, but in the end, for example, here it no longer have the ability to foreseeing the free like flow or the dissipation of the traffic wave.
Can you remind us the time duration length, the size of the x-axis? It's like 5 hours?
Oh, 4 hours. Oh, wait, 4 miles, 3 hours.
So you're doing forward prediction of 4 hours of traffic. You're trying to predict traffic accurately 4 hours from now, over 3 miles.
Yes. 3 hours of 4 miles. Yeah.
Got it.
Yeah.
Is it fundamentally predictable or unpredictable? I think a follow-up question to Professor.
I think it depends on how fine the granularity is.
Right.
Because right now, visually, you see those colors is just to represent the density, right? And the color itself, like green to red, actually, like they can be really large, like real agreed.
Yeah, but my question I think is more on those inherent randomness or stochasticity you may expect in real life, I think. But anyways, maybe move forward, maybe 5 minutes.
Okay,
I'm
sure.
sorry. Yeah.
5 minutes, is enough. It's close to the end. So like, just want to summarize about this really amazing like neural solver for hyperbolic PDEs. So we can actually match the computational cost of first order finite volume schemes. And it's built and tested on the same stencils used by the standard finite volume methods. And it can be easily extended to higher order schemes in both space and time, as I showcased before. And it supports both supervised and unsupervised training. Although like supervised performs better because it knows about like the solutions, and unsupervised use the weak formulation. And it can capture entropy solutions in both approaches. It outperforms all known finite volume schemes across multiple flux functions, and it outperforms all numerical baselines on traffic field data. So actually, I also want to mention that hyperbolic PDEs, they are not just on traffic flows, they are everywhere. For example, ocean waves, for example, shock wave that like trail a supersonic jet or so. So I can definitely foresee our method can be easily extended and like to apply on several different other or even higher order PDEs. For example, as I mentioned before, ARZ model, which is a second order traffic model, or like some shallow water equations like Saint-Venant equations or Navier-Stokes equations. And in summarize, I want to like kind of going back to the 3 pillars of my research. So I really like value the like cohesive pipeline of this, which is starting with the modeling and then like try to do some like steer the system with the minimal intervention with some control and safety algorithms. And I really value that we should design the algorithm that can tackle the real world problems that can bring back to the experimental validation to show our algorithms robustness and safety. And in today's talk, I really want to thanks to my main contributors all over there. There are like amazing student contributors and also a lot of like I got a lot of mentorship from all those PIs. And also I want to acknowledge to the funding resources I received. And thank you so much and welcome to the end.
And Zhe Fu is in person here, and I see Xiaoyang is on Zoom.
Yes,
Yeah,
thank you so much for your support.
All right, so thank you, Jeb. That's a fantastic presentation. Let me briefly summarize that. Today's talk, the bulk of it was really about numerical methods enhanced with neural networks to solve nonlinear PDs. But the broader context was, why do we care about doing this? It was motivation to predict traffic dynamics, right? And so you shared this kind of vision of this challenge of mixed autonomy, where we have some automated vehicles interacting with human-driven vehicles. You talked about the challenge of modeling, control, and then deployment. And it was very interesting that you said, reflect. and I say, actually, really the key scientific problem is on modeling, and if we're able to suppress stop and go waves with automation and connectivity, we need to be able to predict traffic flow accurately, which ultimately comes down to accurately solving or predicting the dynamics of traffic flow. Yeah, so super fantastic. I enjoyed every second of this. And I'll stop my summary there and open the floor to any questions.
I don't really have a question, I have a comment, more than a question. Which relates to this idea of using autonomous vehicles or even partially autonomous vehicles to train human drivers. I like the flipping of the dynamic of training AI to using AI to train humans in this regard. And particularly, I think there's broader application than you're recognizing here. There's application beyond just stop and go waves. There's also applications for training for safety. And training for safety, particularly in like inclement weather events and other opportunities in that regard. So I would encourage you to think beyond the problems that you are currently addressing to broader societal impacts that could come from this type of methodology. And I don't mean the mathematical methodology, I mean the methodology of actually incorporating autonomous vehicles into mixed fleets, into a mixed traffic environment. I think there's a real promise there, and I want to encourage you to keep looking into that.
That's a really, really good like feedback and like the insight that I can spend the impact of my work. Thank you so much, Mike.
Great. Great.
Maybe I ask a question at a very high level, talk about use pins to solve PDE. I think there are actually two distinct questions I want you to kind of like clarify some difference between them. First is, I think you mentioned the emphasis here is how can we use pins to solve this PDE numerically more accurately or more efficiently. But I think there's also another question is what specific kind of form of PDE we should use to characterize or model the traffic flow. I think you also mentioned there are at least 3 versions or 3 generations of PDE characterizing this. Can PIN help also to this end? That is, find a better form, like solve those potential model mismatch problem, not just about the accuracy to solve a known PDE form.
That's a really, really good question. And I'm super happy that you mentioned that because that points out to our core contribution, which is I always emphasize we use the neural network to approximate the numerical flux between these 2 cells. And in the PDE itself, it actually always used the handcrafted or the schemes. But our neural network, because in the supervised setting, it keeps trying to like match the pattern, what's really going on in the systems. And I think through our analysis, those first of all, those like handcrafted numerical schemes, they are usually monotonally like, I think it's monotonally, yes. And but like the result that we learned from the neural network, it actually captured the different pattern, which means inherently it's not perfectly matches with the PDE model that we proposed. I think that's exactly gave us the flexibility that we go beyond the PDE, which is the pre-assumption that we made for the systems. So yes, I agree, like the future extension could even be like through using this method while we are in that framework or in this architecture, can we actually propose even more like closer to the real world situation or the system dynamics PD? Maybe it's not a PDE or something, PDE plus, just like a new model.
Great. Maybe.
Yeah, small question on some details. Like you mentioned, we were using 5 time steps times 5 space steps. So why 5 times 5? Why not like 4 times 6?
Oh, yeah, that's a really good point. We always pick the odd number because at the very beginning, as I show, for the like if we want to like for the first order PDEs, first order final model method, we need the left middle and right to predict the next time step of the middle value.
Then why not 3 times 5?
Or 3 times 5?
Yeah, I mean, like, why you choose 5 this number, and like, is it always better to have, like, include larger time steps? Like, is 5 times 5, like, would 7 times 7 be better?
Yeah, like, maybe you can also like observe that for the results for the I-24 motion data, we actually use 11 times 11, not 5 times 5. So like, I think it's related to the hyperparameter tuning. Some numbers, they just work fine, but like, some numbers, if it is too small, maybe it didn't fit, like in terms of the data set scale, like 5 times 5, actually, when we try to use that for the I-24 motion data, is not enough. So we increase it to 11 times 11, but we didn't try to like compare with 11 times 11 or 13 times 13. Maybe they are like similar.
Yeah, I imagine there's diminishing returns. We have one question online and then we'll close it. Wunu, would you like to unmute and ask your question?
Or maybe Pascal, you can ask on behalf.
Sure, I'll ask on behalf. So the question is, now that you have this new method, this neural finite volume for traffic flow prediction, what's your vision for how that determines how you set the speed for the autonomous vehicles or the connected automated vehicles to help promote better human behavior and I think smooth traffic flow?
Yeah, that's a really amazing question because that directly leads me to my next step for this research. Because I mentioned like I was highly motivated with this physics informed machine learning work because I reflect what's going on in the previous project and I realize how important it is. So with a better and more accurate predictions, I can have the ability to know what exactly will going on in the future. That gave me more accurate information so that the target speed that I design can be more like accurate and effective for all the vehicles to like conduct. So I think that's the brief answer to that question. And actually, the next step I will do is exactly I will try to validate if it is true in the simulations.
Great, thank you. All right, let's get next.
Thank you. Slide. Yeah. So before we end, again, we have live refreshment. So we hope you can also stay here working. And about our next speaker, page 4. Yeah, Joy, if you can go page 4. We are going to have next speaker next Monday, Devansh Jalota. He was actually a Berkeley undergrad. Then he went to Stanford for his PhD. When he was at Berkeley, I think he actually worked with Professor Byron, who is also Zhe's advisor.
He just also worked in eCal too.
Oh, I see. And I think he just graduated the past summer. Currently is a postdoctoral fellow at Columbia University, and he is an incoming assistant professor at Georgia Tech, the industrial engineering program. If you don't know, I think it's often ranked as #1 industrial engineering program in the US. And we are very excited to have him to talk about algorithmic sustainability for resource allocation in large-scale societal technical systems. So please join us either in person or online next Monday. See you next time. Thank you.